طيب, we are continuing inshallah on our study of encryption systems. Today we will discuss the first type of cryptographic systems. It's called symmetric cryptography. The word symmetric means that there is one single key which is used by both the encryption side and the decryption side of the system, and that key is shared between the sender and the receiver. So they both have somehow to have access to that key, and that key needs to be hidden from any unauthorized person. In this case, an attacker should not know the key. If the key is known to an attacker, the system is broken down and no further secure communication can happen. Okay. We call that symmetric cryptography. Now there is another type of cryptography called asymmetric, where the key used by the transmitter is different from the key used by the receiver. And that's actually most of what current communication systems are using. This doesn't mean that symmetric cryptography is no longer used. It is still used in certain applications, and it is still a very strong encryption method. Its only challenge is, from a practical point of view, how do you make sure that you can protect the key, and you make sure also that that key is available somehow to the sender and the receiver. Okay, so these are kind of two contradicting, because if you generate the key somewhere and then you send it to the sender or the receiver, there is a chance that someone will capture it on the transmission channel. So you have to find another way other than sending the key on the transmission channel, and that's the main challenge in symmetric cryptography. Okay, we'll start. The first part today is about some definitions and concepts, just so that when we mention those as we go through the lecture, they don't sound very alien or very strange. Okay, there is an expression called plain text. This is your actual information before encryption. So your actual information, typically you are sending some text in a particular language, right? Before encrypting that, the message is called a plain text message. Okay. Now, once you apply encryption to the message, it becomes a cipher text. Okay. So plain text is without encryption. Cipher text is the encrypted message itself, which is what you typically send over the channel, because before sending, you make sure you encrypt and then you send. Okay. The process of changing plain text to cipher text, so the process of encryption, is called enciphering or encryption. So we call that encrypting a message, encryption process, enciphering process. All these are for the same process. The process of removing the encryption is called deciphering or decryption. Okay? And then the the area of study of encryption, decryption methods, how you perform encryption and decryption, and how you make sure that your communication system is secured using encryption. This whole area of study is called cryptography. That's what we will focus on in the next few lectures of this course. Okay. And then the system that performs the encryption and the decryption is called a cryptographic system, or sometimes also they call it a cipher. Okay, so cryptography is the area of study. The actual operation of encryption and decryption combined together is called cryptographic system. And in many cases, the cryptographic system is not by itself. We include with that also the existence of attacker. We mentioned earlier when we started this course that when you study security, you have to also consider potential threats. What are the threats to your system? How it can be attacked so that you can protect the system. So cryptographic system typically also includes not only the encryption and decryption or enciphering and deciphering algorithms, but also includes the existence of a crypt analysis. Okay? Crypt analysis is the technique used to break the cryptographic system. Okay? So if someone is trying to break the system without having access to the key, without really getting the key somehow, then that person is performing crypt analysis of that cryptographic system. And when they succeed, they manage to get the key somehow from the exchanged messages, okay? And then the area of cryptography with crypt analysis, rather than being called cryptography only, they call that cryptology. That's a very technical difference. I don't mind like confusing those together, it doesn't matter. But the more important ones are what's a plain text, what's a ciphertext, what's an encryption or enciphering process, what's a decryption or deciphering process, what's a crypt analysis, and a cryptographic system, what does it entail, what does it contain, okay? Sometimes rather than calling it a cryptographic system, they call it a cipher system or just a cipher. This means this includes both encryption, decryption, as well as in many cases the existence of crypt analysis as well, okay? Here is a simplified model for symmetric encryption. Remember, symmetric encryption mandates that there is a single key, right, which is being used by both the transmitter or the sender or the encryption algorithm, and the same key somehow is available to the trusted receiver to be used for the decryption or the deciphering algorithm on the other end of the communication system, right? Now notice that this system, the simplified one that we see right here, does not include the crypt analysis part, the attacker part, but in a couple of slides you will see another one which incorporates the attacker into the story, okay? So let's look what does a symmetric encryption or symmetric cipher system includes, okay? Data, this is just the plain text coming from the source, the message that I need to send, an email, an image, a command, whatever, okay? And then we call that, typically we call it X, the actual message, plain text without any encryption. Then we apply some function, okay? That function, typically we call it E, the encryption function, to that message X using the key. So that's why E here is applied to X and the key. You don't just apply a function to the plain text message, but you have also to incorporate the key into the story, okay? Now, the output of mixing the plain text with the key using a certain algorithm, that's the encryption algorithm, is gonna be the ciphertext, the encrypted message itself. That's what gets, we call that Y, and that's what gets transmitted over the communication channel, right? And then at the receiver side, the intended receiver side, there is a decryption algorithm, call it D for decryption. Again, that's another function that uses the key and the ciphertext, because that's the input that it gets. It gets the ciphertext from the channel at the receiver side, and it also should have access to the key. Mixing those together using the decryption algorithm, it should be able to retrieve the original plain text message X, and then that plain text is processed somehow at the receiver side, okay? Now, it's always assumed in any encryption system, whether it's symmetric or asymmetric or whatever, in any cipher system, in any encryption system, okay, that an attacker, someone from outside the system, so not the trusted sender and the receiver, someone other than Alice and Bob, okay, Eve or not, anyone else, intended attacker or someone who's just listening to the system, by default, because they can listen to the communication channel, then they have access to the ciphertext. I can always see the encrypted messages going around, okay? Moreover, in most of available communication systems, like for example your cell phone, if it's using 4G, 4G uses very well-known encryption algorithm. So the function E itself and how it mixes the key with the plain text message is always known. You do not really protect your system by hiding the details of your function, because typically these functions are standardized, and worst case scenario, they can be always discovered by analyzing how the device works, right? If I just buy one of these devices from the market and I test the hardware extensively enough, I can figure out what encryption function it performs. So where does the protection come from? It comes from not knowing the key, right? So the method of encryption itself, how I mix the key with the message, is assumed to be known even to the attacker. The only thing hidden from the attacker is the encryption key. And this is where all your security resides in, okay? So again, you are not hiding the signal over the channel. Anyone can listen to the signal, and that signal will include the encrypted messages, the ciphertext. Okay? Not only that, because encryption methods are standardized functions, right? So it's also assumed that any attacker, if I know that I'm attacking a Wi-Fi, I know what's the encryption function in the Wi-Fi. The only missing piece is the key, right? So these functions E and D are well known as well because they are standard functions, okay? And they are known to the attacker because the attacker knows what he or she is going to attack, okay? The only missing piece that the attacker should not know, and if it's known, the system breaks down, is the key. Okay, so this is clear. In any system, we do not assume protection by hiding the encryption algorithm because that's very difficult to hide. By the way, why it's difficult to hide the encryption algorithm? Because designing an algorithm which is robust enough is very difficult. So typically, to guarantee that a particular algorithm is really secure enough, in the security community, some people design that algorithm, right? And then share it publicly to the community and say, test this as much as you can and tell me if you can find loopholes or weakness points in this encryption method, right? And this is the only way actually to get a feedback to tell you whether your encryption algorithm is secure enough or not. Okay? After you guarantee that the algorithm itself is secure enough, the hiding part is only the key. You only hide the key. Okay? So that's why also trying to design an encryption method which is secure by hiding how the algorithm works is impractical.
But if the hacker know the algorithm, the encryption algorithm, and know its holes and everything.
Yeah, of course. If it knows it holes, it can be attacked. But then again, you don't put something out there into systems before you test it to make sure there are no holes in the algorithm itself. Okay? Typically, there are holes, but they are very difficult to discover. And since they are difficult to discover, the system is secure enough until it breaks down at some point. Okay? We will see that through the evolution of encryption systems, things were very nice at the beginning, and then people discover a particular weakness, then this system collapses. We go to the next system, people find another weakness, system collapses, we go, and it keeps on developing with time. Okay? So yes, again, there is nothing that's 100% bulletproof until today, but it's always getting better and better, and also attackers are getting better and better. Okay, so they keep running after each other. Okay, so just again, this is the whole system end to end, and it's only missing the attacker. We will see it in the next more detailed figure of a cryptographic system or an encryption system or a cipher system, right? And the other thing is, it's always assumed that the attacker, anyone who wants to attack this system, can actually get access to the ciphertext because it's available over there on the channel, the encrypted messages. And they know the encryption algorithm. The only thing that they don't know is the key for the encryption-decryption process. So the main protection comes from the privacy of the key. Okay? There are two requirements for securing or for secure use of conventional encryption. Okay, the two requirements are, we mentioned one of them already, right? Which is that sender and receiver must have obtained copies of the secret key in a secure fashion and must keep the key secure. That's an important requirement. So somehow, in a symmetric encryption system, the sender and the receiver, the two trusted parties, have access to the key somehow outside the communication channel. Okay, one childish way to do this would be that you decide on your key today, and then you write it on a piece of paper. You give it to your friend or colleague or a delivery man, and he carries that envelope closed, goes to the other side, share the key for today with the other party. That's totally outside the communication channel, right? Again, if that delivery guy is not trusted, you can lose the key somehow, or he or she can open the envelope and reveal the key. But anyways, just to give you an example, and that's the main challenge in any symmetric encryption system. How do you share the key? There are two ways to do this. Either the key is generated by the transmitter, and there is some very slow but secure channel between the two parties, other than the communication channel. That's one way. Or the other way, which is more common when the days of mass use of symmetric cipher was there were trusted entities, trusted parties, that have particular, very secure and complicated access mechanism to authenticate a sender and a receiver, and then when it guarantees that these are two trusted parties that needs to talk to each other, it gives the key to both of them only. Nobody else can get access to that keys. They were called, an example of that nowadays is when you do digital signature. You typically go to a trusted website, like Adobe website, for example, and you ask to register for your own digital signature, asks you for some verifications, double check these verifications, and then generates a particular file for you that is sent to you over a very secure channel, typically internet, but in a very secure way. And then you keep that file on your device. Nobody else has access to it. And you use it always to identify yourself using the key in that signature. That's an example how a key can be distributed using a central distribution unit. Okay? Anyways, yes?
Secured like the channels for banks account and those.
Sorry?
Is it secure like the communication for the channels of the bank accounts and
Yeah, but again, even bank accounts, the actual channel that carries the transaction should not be used to carry the keys again, right? Because that's the one that carries the information that can be attacked. The keys should go somewhere else or be distributed in some other way, okay? This is for the second requirement. The first requirement is called strong encryption requirement, right? So there are two important requirements for any symmetric cipher system. The second one is that the key is private only to the sender and receiver, and nobody else should have access to it. The first requirement is that the encryption algorithm or the encryption system is strong. What does it mean to be strong? Okay. Well, there are two ways to figure out what's strong. The first way is very theoretical. Remember when we studied the information theoretic secrecy, we talked about, you remember, the one-time pad, right? Where you generate a key, the key has to be randomly generated, independent from the message, right? And then that key has to be either equal to the length of the message or longer, and you generate for every message, you generate a new key. Practically, very difficult to do, but if you do that, you guarantee perfect secrecy. And in that case, your encryption is really secure. But, as we said, practically, you cannot really do this. What is the other alternative? The other alternative is to do something called practical secrecy or practical cryptography. In that case, a strong encryption algorithm has to satisfy one of two requirements, either the first or the second, or it can actually satisfy both, but that's not easy to do, okay? These requirements are either that the cost of breaking the system, okay, the crypt system, okay, is greater than the benefit. And it has to be really much greater than. So in order to break that bank transaction, I have to use a method that costs me per usage 1,000 riyal. But when I break the transaction, I only gain 100 riyal. Nobody's gonna do this, right? If every time I have to break the transaction, I have to pay someone 1,000 riyal, and if I know that this transaction is worth only 100 riyal, I'm not gonna do it. Because every time I'm losing 900 riyal, right? So that's one thing that makes the system secure enough or strong if the cost of breaking it is much higher than the benefit that you will get from breaking the system. Or the other alternative is the time, we discussed this earlier at one point, okay, to break the crypt system is much larger than the lifetime useful, they call it useful, lifetime of information, right? So in order to break the, I mentioned that example one time earlier, right? In order to break the communication between two army battalions, for example, from the enemy, which that information carries, for example, what kind of weapons they have right now in the battlefield and where are their location. It takes me about a couple of years to break that system, to actually decrypt the message. But when I get the information, so I got the information, it took me a couple of years to break it down. I found out where they were 2 years ago. Is this gonna be useful? Not useful anymore. Now they are probably somewhere else and they have totally different kind of weapons, right? So again, the time that I use, the time consumed until I break the system is much larger than the useful lifetime of the information. In that case, the system is strong enough, because I don't care if people break the information or break the system later on. I only care about protecting the information for a certain duration of time, right? And if I manage to do that, then I'm strong enough, right? So that any strong cryptographic algorithm has to achieve either 1 or 2. Otherwise, the system is not a strong encryption system, because this means that people can actually get access to the information when it is still useful, or people can get benefit from accessing the information higher than the cost that they pay to get that, so they will do it. They will break my system, okay? So that's the definition of a strong encryption algorithm. Any questions so far?
I think the definition for this, it can be like a reliable system.
Sorry?
It has reliability.
What has a reliability?
The algorithm itself,
You mean,
the cost and the time.
are you saying that this is the interpretation of what we mentioned right now? To some extent, yes. But again, reliability sounds like strength, right? It doesn't really have, like, what do you mean by reliability? How do you measure that reliability? So when we mention the details of saying it's either that the cost of breaking is higher than the benefit, or that the time to break it is more than, we specify how you can quantify this, right? So now you can quantify this by saying, okay, if someone wants to break my system, here is the loss that I will get from breaking the system. Here is the amount of loss that they incur to break my system. If I manage, and that loss can be measured, for example, by number of computations or energy consumption or whatever, okay? And then if I manage to make sure that they have to really spend much more than what I lose or what they gain, then that's the point where I have to stop, right? It's enough. Now my protection now is good. Similarly, if the information is time sensitive, if I manage to make an encryption algorithm that requires at least a much longer, like requires months, for example, to break using current computational capability, while the information needs to be protected for a couple of days. Then if I manage that computationally it's strong enough, that's it, right? I stop there, okay? So you need something quantifiable. The word reliability needs a defined measure. Which measure you will use for reliability, right? Okay. Any other questions? Here is the more detailed system, very similar to what we discussed earlier. So we have here the plain text coming from the message source, which is X. It goes through an encryption algorithm, E, that uses the key from a particular key source. It can be either generated by the transmitter, or it can be generated by some trusted entity. And in both cases, it has to be given to both sides. It's either existing already here and has to be given to the other one through some independent secure channel, different from the communication channel, okay? And then there is the decryption side with the decryption algorithm D of K and Y, producing X at the output of the decryption, and then the data is consumed at the destination. In addition to this, there is some cryptanalyst, some attacker, some eavesdropper who's trying at every point in time, using the available cipher text across the channel and knowing the encryption algorithm but not knowing the key, that attacker is eventually trying to figure out what's the key. And if it manages to figure the key, it's definitely gonna be able to read my plain text messages, because it's going to be able to decrypt the messages going across the channel, okay? That's the overall crypto system that we work on for the symmetric case. Okay, for the asymmetric, we will see something different in the future lectures, okay? Now, categorizing cryptographic systems. So today, for example, we discussed the categorization depending on symmetric and asymmetric, this one. There are also other ways to categorize the function of cryptography, the cryptographic system. Remember, in the case of symmetric, there is a single key, which is secret, and it's shared between the transmitter and the receiver, and nobody else knows about that key. For asymmetric key system, there are two keys, one used by the sender, one used by the receiver, right? And the one used by the sender is typically called public key. The one used by the receiver is a private key, right? And So again, one is kept secret, one everyone knows about it, okay? And then the system, again, because it doesn't really use a single key, there is no need for key distribution. The key is generated somehow at the party that controls the communication, and it doesn't need to, that's the private key, and it doesn't need to share it with anyone else. The one which is shared with everyone is the public key only, okay? In that case, there is some mathematical relation between the private key and the public key. Don't get intrigued by this system. We will discuss it in a few lectures. Focus today for the symmetric case, okay? Because I know it's very interesting. How does this work? But we will see in a few lectures, okay? Yes?
You have mentioned before about the edge channel. I don't remember the name, but you said about the edge, like the transmitter know the edge and the receiver know the edge.
That was one way of using some physical layer property which is common between the transmitter and the receiver to generate the same shared key.
Yeah, so this can be like symmetric.
That's a symmetric case, yeah, because again, here both of them are generating the same key at the same time and using it, one for encryption, the other for decryption, but they capitalize on something that allows them to do this without having to exchange the keys with each other, okay? That's still a single key because both of them are using the same key, okay? Okay, other ways of categorization. There is one way that talks about whether you encrypt your data as it goes through one element by element. So for example, if it's a text, then letter by letter, you encrypt each one, right? If it's a stream of bits, then every bit is encrypted individually, okay? As opposed to, you take a group of messages, you construct a block, and then you encrypt this whole block and you send it. And then you go to the next, take a full block, encrypt the whole block together and send it. The second method is called block cipher. This is the more common method nowadays in communication systems, but still stream cipher, the one that does it one message by one message, not a block of messages, still being used. And typically, you can modify the block cipher somehow so that effectively it acts as a stream cipher, okay? But generally speaking, these are two different categories of encryption methods, block cipher and stream cipher, okay? Another way of categorizing encryption and decryption operation is what does the function, remember that function E that I talked about that does the encryption and then the corresponding 1D that does the decryption, what does it do exactly to your message? There are only two possible categories of operations on your message. Of course, you do those using the key and the function. So the function uses the key somehow to perform some change on your message, which is called the encryption. There are only two ways. Either by substituting, so for example, when I'm sending letters, for the letter A, I will always remove it and replace it by the letter Z. That's called substitution. Every time I need to send A, I'm gonna remove that and replace it by Z. And then the receiver knows that any Z that it receives should be replaced back to an A, right? And the same for the other letters. That's called substitution, okay? Or the other is, I have the blocks, the elements of the data that I want to transmit. What I only do is, I'm not changing the values, I'm rearranging them, right? So that's called a transposition operation. So only one of two operations can be performed on encryption, and then the opposite of that is going to be performed in the decryption. Either substitution, removing every message and replacing it by another message according to a particular key and a particular algorithm, or a transposition. Every message stays in what I transmit, but I reorder them. Again, imagine if you have like one line of a sentence, and then you take the letters and you randomly reorder them. Anyone who reads that will not be able to figure out what was your message, right? It's just random set of letters, one after the other. What were the keywords? What were the words, in that? And what does it mean? Nobody's going to be able to do that unless they manage to rearrange, right? Similarly, if it's substituted, nobody's going to be able to read the original message unless they can manage to desubstitute, to recover it back, right? In both cases, whether you do substitution or transposition, it's based on a particular key. We will see examples of both of those as we go through the lecture today, inshallah, okay? So for the rest of the lecture today, we are talking about symmetric. So we use single key, and that's the category of what we were talking about for today and also next lecture. And we'll be focused on stream ciphers. So we will discuss always one message at a time. We are not talking about collecting a big block of messages and then encrypting that, going to the next. In the coming lectures, inshallah, we'll talk a little bit about block cipher because that's the more modern approach to encryption. We will address both some substitution methods and some transposition methods so that you can see the variations. We'll start by very basic ciphers, like the oldest encryption method that was used, and we always get the name of that guy for something, right? So it's called the Caesar cipher. And that goes back to Julius Caesar, the guy of the Roman, okay? Who also is famous for the Caesarean operation, because he's the one who like cut his wife to get the baby. But he did it in a very brutal way, so he did not do it in a surgical way, okay? So anyways, so Caesar was the first one to do the ciphering operation, and we'll see today an example of the Caesar cipher. Before going to that, we'll just discuss the idea of cryptanalysis, the idea of attacking. Attack methods can be categorized into two categories mainly, okay? Either brute force attack. Brute force means that you try all the possible available combinations until you break the system. So for example, if you know that the key of the encryption is going to be one of 10 possible values, then you read the text, the cipher text going across, and then you try the first value and you try to remember, you know the operation. You always know what's the function, right? You just need to guess what's the key. So you try the first possible value. It doesn't give you something meaningful for the same cipher text that you stored. You try the second possible value. You keep on doing this until you reach, when you see something that's really readable, you know, okay, this is the key. Now, once you know the key, any incoming message, you will start decrypting it with the correct key every time, right? That's called brute force. What does prevent brute force from succeeding? When you use larger keys, which means that more possible values for the key. That's why when we talk about strong encryption systems, we start talking from a key which is at least 256 bits. How many possible values there for the key? If we are using 256 bits, 2 to the power 256. What does this result in? Very big number, right? Yeah. So the number of possible values in that case is a very large number. And if you are gonna apply brute force to figure out what's the key, probably by the time you figure the key being used right now, the information is like a couple of years old or 6 years old. And probably also by that time, the key value has changed. It's not the same all the time. Every few days or weeks or months, the key is gonna change. So by the time you catch the key, you already have the key changed, so it's a losing battle, right? Okay. So brute force does not work when you have larger keys, when you have larger number of possible values for the key. Now, what if the cryptographic system, the cipher system, is using a large key? Is it now very well protected and cannot be broken? No. There is another way to attack encryption systems using something called the cryptanalysis. The cryptanalysis is an approach that uses some statistics about the plain text message that you know, and then based on that, and if the cipher system does not disrupt these statistics a lot, you should be able to break the system. I'll give you an example on this as we go through the lecture, inshallah. But to simplify this, if I know that those two systems are communicating messages in English language, okay? And I know that the most common letter in the English language is the letter E, because if you go to books that analyzes the English language, you will figure out that the most used letter is the letter E. And then after that, the letter T, if I remember, and then A, and then so several. There's statistics that tells you what's the most used, what's the next one, and so on, right? Now, no matter what they do in terms of changing, for example, the letter E every time to some other letter, if they keep that change fixed, so always E is gonna be changed to something else. When I see the cipher message going in front of me, for example, I will notice that the letter P is repeating a lot, more than all the other letters. after collecting a good number of messages, then I will figure out if it's the most repeated, it must be the replacement of E. So now I've broken what was the encryption of E. E is always changed in this cipher to be the letter P. Then I go to the next most repeated one, and I figure out maybe it was the letter, for example, L, and I see that the next high probable one should be the letter T, so it must be that L is the replacement of T. And so on until I can keep doing this with some trials and errors, but not like the brute force. And then I can break the system eventually, because I will manage to get all the replacements that have been performed. And once I know that, whenever I get a message in front of me, I will be able to break it down. I will be able to figure out the original message, okay? So that's called decrypt analysis attack, okay? Anyone has any questions before we move on?
What if the messages have different probability than the language itself?
Yeah, this is where the encryption is strong. And then we will see that you will always retain something. And then how much you retain and how much effort is needed to break it down, that's what we will go through in the next few slides, okay? Yeah. Okay. Also related to attacks, there are different types of attacks based on the knowledge of the attacker. So there is the ciphertext only attack. It means that the attacker doesn't know anything about the data being exchanged on the channel, except that he or she can see the ciphertext. That's it, okay? In this case, of course, this is the hardest job for the attacker. But still, as we mentioned, maybe with brute force, if the encryption system is not strong enough, with some brute force approach, they can manage to break it down, okay? Now, the other option is they don't just read the ciphertext, but they also know some plain text, okay? They know that this type of communication has to include certain words or certain messages. I'll give you an example. If I know that those two entities most of the time are exchanging PDF files in their communication, right? I know that any PDF file has a standard format that includes some header, which is the same for all PDF files, just to identify this file as a PDF to the computer, right? So I know that these messages going and coming will repeatedly include a particular plain text, which is encrypted, right? So I will look for a pattern that's much repeated, and then try to see if this pattern can be converted to the header of the PDF file. And if I manage to do that, I know that this pattern maps to that, and that gives me a little bit more information that I can use it for something else and so on. So knowing some possible plain text about the communication gives you more power to break the system as an attacker, okay? Not only just any plain text, which is this case, sometimes I can actually know exactly certain useful plain texts in the communication system. An example of that is more or less knowing that Wi-Fi systems have certain, for example, repeated headers that are always included. This is what happened in the web, for example, okay? Repeated all the time when you communicate, then I know that this is I know that it repeats even over a certain period of time, right? So I can just be looking for a pattern with periodicity. So that's a little bit more. It's not just some random plain text that I managed to figure out, but it's a well-chosen plain text. So I have a little bit more knowledge about the system. In some cases, rather than knowing the plain text and then I look for the generated ciphertext, I know that a particular ciphertext has to be transmitted between those two parties, okay? I know, for example, that they include an encrypted part of the password, right? So I know that the encryption of the password is always going through this channel, right? And in this case, I know the ciphertext. I don't know the plain text, but I can figure out what's the corresponding plain text. So that's another way of knowing knowledge. This way, the last one, chosen text, means that I know some plain text and their corresponding ciphertext, and I know some ciphertext and their corresponding plain text. So I have a lot of knowledge about that communication system, and accordingly, this is the easiest way where I can break a system. This is the hardest, and in between there is some spectrum, or relates to the knowledge of the attacker about what's happening on that communication system, about the data going through that communication system. Okay. Okay. This is kind of repeated to what we mentioned. Security of any system can be either unconditional. Unconditional is the perfect secrecy situation. We said that this can only be happening with the one-time pad encryption method, according to Shannon, and that's practically very difficult. The other option is computationally secure, and in that case, we said there are two conditions. One of them has to be met, right? This is the more practical case. Either the time is too long, so by the time I break the message, there's no value for that message, or the effort and the cost of breaking the system is much higher than the benefit. So in that case, the system is still computationally secure. It's not really unconditionally secure. Why we call it computationally rather than unconditionally? Unconditionally means no matter how much computational power the attacker has, even if they have the super computer and the fastest computational method, they cannot still break the system, right? While here for computationally secure, it's conditioned that now this system is secure, but if the advancements of computation creates much faster computers, then this means either the cost will go down or the time will go down, and at some point my system will break. Okay? So in these cases, it all depends on the available computational power. One example of that is the hype that you hear about, which is a true hype, about the quantum computing methods, right? The idea of quantum computing being a threat on encryption systems is a true idea conditional on one thing, that we reach at some point the point where quantum computers are efficient enough as they should be. Until today, right, actual quantum computers, they suffer from two issues. Number one, they have very high cost because of the need either to be cooled down or created from very advanced material, right? And accordingly, the size, the number of bits, they call them qubits in that case, per computation is still very small compared to classical computing, right? The other problem with quantum computing is that quantum computing relies totally on probabilistic approaches. So here is this example that people mock the quantum computing about. They say, okay, go to a classical computer, say 1 + 1 =, and the classical computer will tell you 2. That's it, end of the story. Go to a quantum computer, and that's true actually, okay? That's true pending new advancements, okay? Say 1 + 1 =, and then it will tell you 2 with probability 0.6, and 1.5 with probability 0.1, and 1 with probability 0.09, and 2.5 with probability, and come on, I mean 1 + 1 = 2. What's this? Which one should I choose, right? Okay, so that is called, because of that randomness, there is a computational error that can always happen in quantum computing. There is a counter method that is being developed. Last couple of years, there was a big breakthrough on that, especially from IBM and Google, okay, which is called computational error correction mechanisms. So people are coming up with some redundancy, similar to what you do in communication system. So they add some redundant qubits that are functions of the other computed qubits, such that they can correct those probabilistic errors that can happen in computation, and they can produce like a 100% or very close to 100% reliable results for the computation. But again, those consume some of the available qubit capacity, and then we keep on fighting. Like I increase, then I need more protection. So still the problem is not advancing, or the technology is not. So why people are talking about post-quantum encryption nowadays, even though we don't have that much efficient. So if you ask me, current quantum computers, they cannot break our encryption that we use nowadays, the advanced encryption methods, okay? So what's the problem? The problem is preventing against an attack called store today, process later. So what's happening right now, the fight between big governments and big entities and so on, is, okay, I will listen to your encrypted data, I will keep storing it, with the hope that, and I'll keep it in a storage, with the hope that while I'm advancing my computational methods, maybe a year, 2 years, 3 years, and then once I reach the efficient point, I will bring your data, put it to the computer, it's gonna open the encryption system and give me the actual plain text information. And if that information includes something relevant to national security, which typically stays important for 20 years, 25 years, 50 years, I've managed actually to break something very valuable, right? Or it includes some plans, or it includes sometimes even like commercial wars between big companies, things like that. So that's why they are working nowadays, and they have developed some encryption algorithms that cannot be broken with efficient quantum computers. They call them post-quantum encryption, okay? Not because now the current encryption can be broken, but because we want to make sure that we protect our data now so that it cannot be stored and broken in the future, okay? That's side story, but I think it's very important to know about, okay? Your break. This slide is, again, revisiting the brute force attack. Just tells you a little bit more details about how it happens and why it's not efficient when the key is much larger. The important thing here, okay, is the second part. On average, how long does it take a brute force attack to break your system? On average, it's not gonna be number of trials equal to the possible values of the key. It's gonna be number of trials equal to, on the average, half the possible values of the key, because in some cases you can quickly figure it out. In some cases you have to try almost everything. It's like when you search for something in a stack of papers, right? Sometimes the second paper is the one that you're looking for. Sometimes you have to flip until you reach the last one. And then the average is gonna be, with those short times and those longer times and so on, the average is gonna be that if you do many trials, it's gonna be almost half the size of the stack. So similarly here, half the size of the key, okay? That's the average search time. And then if the key size is really large, like the 256, for example, this half becomes really a large number of trials, and computationally it's gonna take a very long time, okay? Last thing is kind of like a practical hint that for brute force, typically only the trials are not enough. You still need, for example, to know which language they are communicating with so that you can stop when you see the plain text, right? If I assume that these guys are talking in English and then they are communicating in, let's say, even Arabic, right? Then every time I try one of the keys, I'm expecting some English language to appear. It will never appear. So I don't know when did I figure out the key correctly, right? So I have to also have some other knowledge so that the brute force operation can work, okay? Now let's look at the first kind of encryption, starting with that Caesar cipher. And that kind of encryption is the substitution techniques. So the first operation or the first type of functionality of encryption is gonna be using substitution. And the most famous and the oldest is the Caesar cipher. And the Caesar cipher works very simple, but yet at that time it was very efficient. And we will see as we go for advancement that people capitalized on the same idea but got some variations of it to make the cipher more complicated, okay? So how does it work? It works by providing you with a key. The key is going to be any letter that you receive, right? You replace it by which letter? And in that case, the key is going to be that, for example, any letter is replaced by the one that comes, let's say, 3 times after it, okay? So if I get the letter A, I'm not gonna send the letter A, the encrypted letter is gonna be what? 3 times after A is got A, B, the first one, C, D. So for any A, I'm gonna send D. If I want to send the letter H, right? So H is what I want to send, I, J, K. So instead of H, I'm gonna send K, okay? If I want to send the letter Z, now at the end of the alphabet, you round and go back. So from Z, A, B, and then the third one is C. So instead of Z, I'm gonna replace it, substitute it by a C, and so on. So the key here is a single number that tells you how many shifts you have to move from that letter to encrypt the message. You got the idea? It's clear? Okay. And the Caesar cipher was actually with 3 time shifts. But then later on, you can actually change that number, make it 5, make it 10. How many possible keys are there in this case? When we talk about the English alphabets, 26 possible keys, right? Either you can count them as either from 0 to 25 or from 1 to 26. They will give you the same result, right? So either I get the message and I keep it as it is, so there is no shift. So A is sent as A, B is sent as B, C is sent as C, and so on. Or I shift by 1, or I shift by 2. For every letter, I shift by 3 until I shift by 25. Because if I start shifting by 26, I will go back to the same letter, right? By the way, you will see that when we try to express the Caesar cipher mathematically, we'll start using some of the notations that we learned in our modular arithmetic. That's why we learned that chapter, okay? That's one reason. We will also come up with more reasons as we go through. So let's look, for example, at here. This is the message that I want to send, right? That's the plain text message. Meet me after the toga party, okay? And then this is the encrypted version of that message. M is replaced by P. How many letters between M and P? 3, right? So if you start from M, N, O, and then P, right? Then you go to E. E, F, G, H. So E is replaced by H. Same thing here. T. After T, U, V, and then the next one is W. So the T is replaced by a W. And so on. You do the same here. Every letter, you shift by 3 and you replace it. And that's the encrypted, that's the cipher text that you send over the channel. If anyone sees this and they don't know the key, they cannot figure out what was the message, right? Very simple, but it works really nice. Because it ends up with garbage. You don't know what language is this, what's the message, right? But then, because the key here has only 26 possible values, right? If I know that this communication system is using Caesar, we said that any attacker typically knows the method of encryption, but it doesn't know the key. What's a successful attack that I can perform here? Brute force. That's called brute force, right? So the brute force attack. I will capture some messages, like I'll capture this message, for example, okay, which is cipher. And then I try, for every letter, shift back 1, shift back 2, shift back 3. Once I shift back 3, I will see something that makes sense in English, right? So I know now that the key was 3. Broken the system, right? Once I know the key, any coming message, subtract 3 from each letter. And I will get the plain text message. So because the number of possible keys here is very small, the Caesar cipher can be broken just using brute force attack, okay? This, even though this is the case, it stayed actually very efficient for a few hundred years, since the days of Caesar, until people came with like more intelligent mathematical tools, and then they said this guy can be broken very easily, right?
Does it have to be uppercase?
La, upper or lower doesn't matter. So we assume here that upper, just convention, you will see it in the book, that they use uppercase to represent cipher text, and they use lowercase to represent plain text message. So if it's an encrypted message, they put the letters in uppercase, and if it's an original message, they put it in lowercase. But
They are not 26, they are multiplied to.
But again, what does the upper and lower make a difference in terms of understanding the language? It doesn't make any difference. So there is no value of doing this, right? If it makes a difference, that's a different story. But here, it doesn't make a difference. We are talking about English language. If I figure out the text all in uppercase or all in lowercase or some upper and some lower, the same meaning is revealed, right? So it doesn't matter. So I only care about the letters. Upper or lowercase, it doesn't matter. Okay? Maybe you can extend, if you go to another language, for example, Arabic, then the number of possible alphabets is like 28. So in that case, you have a key size of 28, right? If you add the digits, so you are not just sending text, you are sending text as some numbers, then in English, rather than 26, they're going to be 36, right? Because the numbers 1, 2, 3, including the 0. So 10 more possibilities, right? So that's, I mean, language dependent will tell you what's the size. But for English, it's 26 possible values, okay? Now, if you want to represent what we talked about now, mathematically, then the encryption, the creation of the cipher, which is the encryption that takes the key and the plain text letter, is simply take the plain text, add 3 to it, and calculate the value mod 26. Because why the mod 26? Because, for example, imagine I go to the letter Z like the example that I said, okay? So I take Z, which has a value equal to 26, right? Because it's the letter number 26. And then I add 3 to it, I'm gonna get 29. What's 29? Which letter? So 29 mod 26 is gonna bring me back to letter number 3, which is C, right? So that's why all these operations of the Caesar cipher, because we assume cyclic, at the end of the alphabets, you go back to the start, then the operations are mod the number of the alphabets, okay? So that I can get a number that always maps to a letter. Right? That's why we studied the modular arithmetic earlier, to understand this notation. What does it mean, okay? So generally speaking, the cipher is equal to the letter, added to it the key value, and then you calculate this mod, the size of the alphabet. Mod 26 here, because we have 26 alphabets in the English language. And for the decryption, it's the opposite operation. So you take the cipher, subtract the key to retrieve the original message, and calculate this mod 26 again, okay? And you will be able to recover the original plain text message. Any questions about the Caesar cipher? Why it's weak? Anyone can answer this question? Because the key size is small. Only 26 possible values for the key. How can it be broken in this case? Brute force. Why brute force works? Because the size of the key is small. There are only few possibilities, so quickly I can figure out. Yes, mod 26, because we have to map back. So if we exceed the size of the alphabet, we have to roll back to the start, okay? Here it shows you what will happen when you do that repetitive trials, right? So I will try shift down the letters. I read, this is the cipher message on the channel, the encrypted message. Then I will try the first key 1, subtract 1 from each. I get something that doesn't make sense. So the key is not 1. 2, I get again rubbish. So the key is not 2. When I do 3, I will see that there are words that make sense in English. So I'll figure out that my key is 3. Again, a precondition here is you know at least what's the language of communication. If you don't know it, you don't know where to stop, right? When would you say that it makes sense now if you don't know the language, okay? This is an example of what you can do to a little bit take advantage of this requirement of prior knowledge. One thing that you can do is if you have, for example, a file, a text file, and you want to send that encrypted using Caesar cipher, so instead of just encrypting it as it is, you probably take it through a compression, so you convert it to a zip file. Now it becomes binary, it's no longer text. And then you apply to that every character, which will look like this, right? You apply the shift and you get another rubbish character, you send it to the receiver, and then the receiver knows that it is an encrypted, it's a compressed file, so the receiver needs to decompress first. If the attacker in the middle does not know that you performed encryption, you performed compression, then using brute force, even though the attacker knows that you are using Caesar cipher, using brute force, he or she will always get rubbish, right? They will get something similar to this, but different rubbish letters. So they wouldn't be able to figure out which value of the key was the one used, right? Again, this is not a strong attack, because an intelligent guy would say, okay, after trying for English language, what if they used compression? There are only 3 or 4 ways known for compression using software, zip, tar, jar, all these possibilities. Each one of them has a header which is well known, even known as a binary value. So I will try until I recover a header that makes sense to me. Once I did this, I figured out the key, and I also figured out what was the compression. I will get the data, decompress it, and read it, right? So it's a little bit extra protection, but it's not that much protection, okay? It's based, again, on playing some trick with the method of the encryption, not really protecting the key more, okay? So, but that's, again, one trick that can be played in this situation. Finished with the lecture set of today. I was planning to go into some of the newer slides, but that's fine. We can carry those next time, inshallah.